Have you ever seen a freight train chugging along the tracks, pulling a mile of cargo? It's a pretty impressive sight, but have you thought about what gives these steel behemoths their incredible pulling power? Many modern trains, especially electric ones, are marvels of engineering. They use a fascinating process to turn electricity into motion. Let's break it down, step by step, and see how these electric beasts work. Imagine a regular toy train. You know, the kind that runs on a track with a little plastic engine. Now picture that toy train magnified thousands of times, carrying tons of cargo instead of tiny plastic passengers. That's closer to a real locomotive. Now instead of batteries, imagine it's plugged into a giant power source. That's the basic idea behind an electric locomotive. Electric locomotives get their power from electricity, just like many household appliances. But instead of plugging into a wall outlet, they draw electricity from an external source, like overhead wires or a third rail. This continuous flow of power is what allows them to run for miles and miles without needing to stop and refuel. In the next section, we'll dive deeper into how electricity travels from its source, often miles away, to power these massive machines. To understand how electric locomotives work, we need to start at the source of their power, the electric grid. Think of the grid as a giant network of power lines stretching across the country, like a web of veins and arteries carrying vital energy. Power plants, the heart of the grid, generate electricity using various sources like coal, natural gas, nuclear energy, or renewable sources like solar, wind, or hydro. This electricity is then stepped up to very high voltages by transformers at the power plants. Why high voltage? Because transmitting electricity at high voltage reduces energy loss during transmission. It's like sending a package through an express delivery service instead of regular mail. It gets there faster and more efficiently. These high-voltage power lines carry the electricity over long distances to substations. Think of substations as distribution centers where the voltage is lowered or stepped down to levels suitable for use in homes, businesses, and, you guessed it, electric locomotives. Now that we understand how electricity is generated and transported, we can follow its path directly to the locomotive. In the next section, we'll see how the locomotive receives this power and prepares to use it for motion. Get ready to explore the fascinating world of pantographs and third rails. We've got our power generated and transported at high voltage across the grid. How does an electric locomotive tap into this power grid? There are two main ways: overhead wires or a third rail. Overhead wires or catenary systems are those thick cables above tracks. The locomotive connects using a device called a pantograph. Imagine a metal arm with a sliding contact point at the top. This arm raises to make contact with the overhead wire. The other method is the third rail, a conductor placed alongside the tracks. You've probably seen these in subway systems. The locomotive uses a special contact shoe to draw power from this third rail. Both systems deliver electricity to the locomotive continuously. This constant flow of power gives electric locomotives their advantage. They don't need to stop and refuel like diesel-powered trains, but receiving the electricity is just the first step. This high-voltage power needs to be transformed into a manageable form. That's where transformers come in, the subject of our next section. Get ready to unlock the secrets of these electrical wizards. We've delivered high-voltage electricity to our locomotive through pantographs or a third rail. But this electricity is too powerful for the motors. It's like watering a plant with a fire hose. We need to step down the voltage to make it usable. Locomotives have onboard transformers for this job. Think of a transformer like a car's gear system. It controls voltage and current, stepping it up or down. In locomotives, it steps down high-voltage electricity to a safe level for traction motors. Now, let's explore the heart of the locomotive, the traction motors. These convert electrical energy into mechanical energy, making the train move. Get ready to explore the fascinating world of motors and motion in the next section. Section 5, the heart of the beast: traction motors. We've got our electricity flowing, we've transformed it to a usable voltage, and now it's time to talk about the real stars of the show, the traction motors. These powerful machines are the heart of the electric locomotive, responsible for converting all that electrical energy into the mechanical force that turns the wheels and gets the train moving. Electric motors work on a simple but fascinating principle: electromagnetism. Inside every electric motor you'll find coils of wire and magnets. When electricity flows through these coils, it creates a magnetic field. This magnetic field interacts with the magnetic field of the permanent magnets inside the motor, causing a force that makes the motor's rotor spin. In a locomotive, these special motors are called traction motors. They're designed specifically for the demands of heavy-duty use, capable of generating incredible torque, which is the rotational force that makes the wheels turn. But how does the spinning motion of the motor actually translate into the linear motion of the train? That's where gears and axles come into play, the subject of our next section. Section 6. Turning electricity into motion, how motors make wheels turn. We've got our powerful traction motors energized and spinning, but how does that spinning motion actually translate into the forward movement of a multi-ton locomotive? The answer lies in a clever combination of gears and axles. Remember those toy trains we talked about earlier? Many of them use a simple gear system to transfer power from the motor to the wheels. Electric locomotives utilize a similar principle but on a much larger scale. Each traction motor is connected to the axle of one or more wheels through a system of gears. These gears act like torque multipliers, increasing the rotational force produced by the motor and delivering it to the wheels. It's like having a team of strong individuals pushing a heavy object. The combined effort makes the task much easier. As the traction motors spin, the gears turn the axles, and the wheels, firmly connected to the axles, begin to roll along the tracks. The faster the motors spin, the faster the wheels turn, and the faster the train moves. We've now successfully converted electrical energy into mechanical motion, but there's one crucial element missing: control. How do we regulate the speed and direction of the locomotive? That's where the engineer and the control system come in, the focus of our next section. Section 7. Controlling the beast, the engineer's role. We've got the power, the motors, the gears, and the wheels all working together, but we need a way to control this powerful beast. That's where the engineer and the locomotive's control system come in. Think of the engineer as the conductor of an orchestra, and the locomotive's control system as their instrument. The engineer, from their cab filled with levers, dials, and screens, interacts with the control system to regulate the flow of electricity to the traction motors. By adjusting the controls, the engineer can vary the speed and direction of the locomotive. Want to go faster? Increase the flow of electricity to the motors. Need to slow down? Decrease the flow. Switching directions is simply a matter of reversing the flow of electricity through the motors. Modern locomotives have sophisticated control systems that go beyond basic speed and direction control. These systems monitor various parameters including speed, acceleration, braking, and power consumption, ensuring optimal performance and efficiency. We've now covered all the major components and processes that make an electric locomotive work. But what are the advantages of this technology? Why choose electric over other types of locomotives? Let's delve into the efficiency and environmental benefits in the next section. Section 8. Efficiency in motion. The beauty of electric locomotives. We've seen how electric locomotives work, but what makes them so special? Why are more and more countries investing in this technology? The answer lies in their remarkable efficiency and environmental friendliness. Electric locomotives are incredibly energy efficient compared to their diesel counterparts. Electric motors are inherently more efficient at converting energy into motion, meaning less energy is wasted as heat. Additionally, electric locomotives can utilize regenerative braking. When the train slows down, the motors act as generators, converting the kinetic energy back into electricity, which is then fed back into the grid. It's like getting a little pushback every time you brake. This high efficiency translates into lower operating costs, making electric trains a more economical choice in the long run. Furthermore, electric locomotives produce zero emissions at the point of use. This means cleaner air, especially in urban areas and tunnels, and a smaller carbon footprint, contributing to a healthier planet. The advantages of electric locomotives extend beyond efficiency and environmental benefits. They also offer smoother acceleration, quieter operation, and reduced wear and tear compared to diesel locomotives. As we move towards a more sustainable future, electric locomotives are poised to play an increasingly important role in transportation. In the concluding section, let's recap what we've learned and look ahead at the exciting future of electric train travel. Section 9, Conclusion, A Powerful Future. From the generation of electricity in power plants to the rotation of massive steel wheels, we've journeyed through the fascinating inner workings of electric locomotives. We've seen how these marvels of engineering harness the power of electricity, transforming it into motion with remarkable efficiency and environmental responsibility. Electric locomotives represent a powerful step forward in the evolution of transportation. Their energy efficiency, reduced emissions, and overall performance advantages make them a compelling alternative to traditional diesel-powered trains. As technology continues to advance and the demand for sustainable transportation solutions grows, electric locomotives are poised to play an even greater role in shaping the future of rail travel. The next time you see an electric train gliding silently along the tracks, take a moment to appreciate the intricate dance of energy and engineering that makes it all possible.